Welcome back. Today we're going to be continuing with Chapter 4 with probability, and specifically we're going to be looking at both the addition and the multiplication rule and how they apply to probability problems. Okay, so in this section, we'll be looking at the addition rule, which is a rule that we're going to be using to find the probability of A or B. This is the probability that either A occurs or event B occurs or they both occur. So that's why it's kind of like the union of the two. Or means union, so it's the union of A or B. And the key word for the addition rule is or, as I have it highlighted here. The multiplication rule is going to be where we find the probability of both A and B occurring. Okay, so we want to know the probability when they're both going to be occurring like that, and the key word is and for that. Okay, so we're going to be talking about compound events, and so a compound event is any event combining two or more simple events. So we might have an event of selecting a student, but the simple events might be that we could get a freshman or we could get a sophomore. So when it can be broken down into simpler events, then or it's the combination of a couple simple events, then that's going to be our compound events that we'll be working with. So combining those with or is an example of a compound event. Okay, so the notation for this addition rule, we've got the probability of A or B. So basically what that's saying is in a single trial, and this is really important because when we start looking at problems that are mixed up and we're trying to decide if it's going to be the addition rule or the multiplication rule, if you're selecting a single, making a single selection, then it's more than likely going to be the addition rule, and that's because you're talking about a single trial. So in a single trial, event A occurs or event B occurs or they both occur. So basically, if this is A and this is B, then this overlap here is where they're both occurring. So when we're finding the probability of A or B, we're finding the probability of the combination of all of this combined together here. Okay, so there's a couple ways we can go about this. I like to look at it both formally and intuitively. So the intuitive way here is that basically we have to make sure that we add the outcomes up in such a way that each outcome is only counted once. So like if I were to add everything that's in this purple set here, and then everything that's in this kind of tan colored set here, then what happens is this in the middle, this overlap region is going to get double counted. So we want to make sure that we're not double counting this middle part here as we use this addition rule. Okay, so here's an example that I want to go through, and it kind of leads us into intuitively looking at the addition rule. When you have a table like this and you're asked to find quite a few different probabilities, my recommendation would be to go ahead and total the table in every direction. So if I add all of these up, I'm going to get 625. If I add the girls, I'm going to get 603. And if you ever see that I've added something wrong, please feel free to let me know in an email. I'm definitely not perfect, and that can happen that I add things wrong. If I go across here, this is going to be 250. This one will be 210. This one will be 135. This one will be 215. This one will be 193. And then this one's going to be 225. And then what I like to do is make a little box here in the corner, and I'm kind of running out of room, but that's the total of the whole table here. So either add up across or add up going down. Sometimes I actually like to go both ways just to double check. But if I add up and or across, I get 1228 as the total for this entire table. So when I go to do these probabilities, I have all the information that I need to set this up. So the first one I need to find the probability of a first grader. So if I look, I have 210 first graders, and that's out of a total of 1228. Okay, and remember we want to give our decimals to 3 significant digits. So on that one, it's going to be 0.204. So the probability of a boy, we want to add up all the boys. So we've already done that. So 625 out of 1228. and that is going to give us 0.509 for that probability. Okay, here's where we start getting into some that use the addition rule, because this one we want to get the 4th or 5th graders. Okay, so all we're literally going to do is add up our 4th graders. So we had 193 of those. And then we're going to add up our 5th graders. And so from there, we're going to get our total. And so our total is 418, and that's out of 1228. So if we give that as a decimal, our decimal for that one is going to be 0.340. Okay, if we're looking at the probability here for 3rd grade boys, there's only 125 that are 3rd grade boys. So we're going to do 125 out of 1228. And when I divide that out, I get 0.102. Okay, if we look at the probability of a kindergarten girl, it looks like we've got 130 kindergarten girls. And again, that's out of the 1228. So when I divide that one out, I'm going to get 0.106. And then the last one here is another one with the word or, and this is the kind of the lead in to really talking about the formal definition of the addition rule. We want the probability of a 2nd grader or a boy. So if we look at our 2nd graders, okay, here's our 2nd graders. We've got 135 2nd graders. Okay, so, and then we have, when we look at the boys, we have 625. But we have a little bit of a problem, because if I'm looking at 2nd graders, that's these. And if I'm looking at boys, that's these. So when I write these two totals down, I end up counting 75 twice. So to compensate for that, I'm going to actually subtract the 75, because it got counted here and also here, and we don't need it to be counted twice. So I'm going to subtract it one time, and that gives me 685 out of 1228, so 0.558. I want to mention one other thing. Some people don't really like to do it this way, and as long as you can come up with the answer, I'm not going to make you do it using the formal method. The informal is fine. So basically, if I wanted to do this using the informal method, I would add up the boys, and then I can see that the only additional one I need to pick up is this 60. So I add up the boys and then grab this 60 over here, and that gives me the 685. So there's ways to do it intuitively, and there's ways to do it with the formal definition that I'm going to be showing you shortly. Okay, so the formal addition rule is the probability of A or B is the probability of A, and so that was our 2nd graders. And then the probability of B, that was our boys, minus the probability of A and B, so that was the 2nd grade boys in our previous example. So probability of A plus the probability of B minus the probability of this overlap, okay? So wherever they're overlapping and getting double counted is the part we have to subtract away. And you can kind of see that here. You've got A and you've got B. You've got A and B is this part that gets counted twice, and so we've got to subtract one of those away. Okay, one term that you should be familiar with is disjoint, which in some textbooks will also be referred to as mutually exclusive. That just means that A and B don't overlap. So some occurrences, they're not going to overlap, and they can occur at the same time. So I've got a couple examples here. If you are registered as a Democrat and also registered, or if someone's registered as a Democrat and then someone's registered as a Republican, there can't be any overlap of those two, because you're not allowed to be registered both ways at the same time. So those could not overlap. You can't be a freshman and a senior at the same time. So the disjoint events are those where they can't occur at the same time, and so therefore they're not going to be overlapping. So some of the not disjoints, when we do have an overlap and you can have A and B occurring at the same time. So some examples that are not disjoint. Event A this first example, event A, we randomly select someone taking a statistics course, and event B randomly selects someone who is female. So someone taking a statistics course and someone that's female, obviously these two can overlap because quite a few in this course are both female and taking a statistics course. So we can have an overlap of these two events here. So for our second example here of disjoint, of events that are not disjoint, we have a Wingate student that's selected as a female and a Wingate student is a business major. So obviously these two can overlap also and therefore would not be disjoint. So if I'm totaling my columns, the first column would be 412, 308, 228, 204. And then if I total the rows, this row would be 1004 and this one's going to be 148. And then if I total here either down or across, don't do both unless you're just checking. But this would be the total number of values in this whole table here. It would be 1152. So if I want to look at here the probability of going to restaurant A or C. Okay, here's A and here's C. So I'm just going to add those two together. 412 out of 1152 plus 228 out of 1152. And that's going to give me a total of 640 out of 1152 and give that as a decimal answer would be 0.556. As far as are these events disjoint, here's A and here's C. So we have no overlap, so yes, they are disjoint. This one we want the probability of going to restaurant B or getting an accurate order. Okay, so we want to look at the probability of B plus the probability of an accurate order minus the probability of both B and an accurate order. Okay, so probability of B would be 308 out of 1152. Probability of an accurate order is going to be 1004 out of 1152. And then probability of B and accurate, if we look up here, here's our accurate orders. Here's our B. So the part that gets overlapped is this 255. So that's what we're going to subtract here because it got counted both directions. Okay, so when I do that, I'm going to be at 1057 out of 1152. So I'm going to have 0.918 as my probability. Okay, as far as doing this intuitively, if you want to just add up the accurate orders and then pick up this additional one here for the 53 to represent all of B, then that's another way you could do the problem. Are the events disjoint? They're not disjoint because we do have an overlap here, that overlap being the 255. Okay, so summarizing the addition rule, we look for the word or. And basically we're looking to make sure that we account for everything that's in A and also in B, but we have to be careful that we don't double count anything. Okay, moving on to the multiplication rule. The multiplication rule uses the word and, or another thing I want you to kind of think of is if you have multiple trials or multiple selections. So if I'm selecting 4 people or I'm selecting 10 people, that's an indication that I'm going to use the multiplication rule. So by definition, the probability of A and B is the probability that event A occurs in the first trial and then event B occurs in the second trial. So another notation here is the probability of B given A. This is called conditional probability. And this vertical line here is read as the word given. So it's the probability of B given that A has already occurred. Okay, so that's how we read that. Okay, a few hints I've compiled for the multiplication rule. Look for the word and, sometimes even the word then, because it's almost like it's implied and then something else is going to happen. Used for multiple selections. And then one thing I think will be very helpful as you go forward with this is the number of parentheses is going to be the same as the number of selections. So if you have 5 selections, you're going to have 5 parentheses or the equivalent of 5 parentheses. And you'll understand what I'm talking about when we get a little further into this. Okay, so the intuitive multiplication rule, we just want to make sure that we are multiplying the probabilities and assuming that event A has already occurred and take that into consideration. And this will be demonstrated as we go along. So here's our formal definition for the multiplication rule. The probability of A and B is going to be the probability of A. So this is like that first selection. And then we're going to have the probability of B given A occurred. So here A occurred, and here we're going to find the probability that B occurs given that A has already occurred with that. So a couple terms you need to be familiar with. Independent and dependent are important, just like disjoint and not disjoint were important for the addition rule. Independent and dependent are important for the multiplication rule. So when we're talking about independent, it means that the occurrence of one does not affect the probability of the occurrence of the other. Okay, and this can be applied to more than 2 events. So basically, if we're talking about, say, having children, if you have a boy for the first child, that's not going to affect the probability of having a boy or a girl for the second child. The 2 events are independent of each other. If I'm going to flip a coin 2 or 3 times, each time I flip it is independent of the others because they're not affecting that. They're not affecting each other. So in some of the problems, one thing to keep in mind for a key word with this is the word with replacement. With replacement just means that once you select the first item, you're going to put it back, and therefore it's not going to be affecting the second item that's being selected. Okay. When you have a situation that's independent, you can simply multiply the 2 probabilities together, and you don't have to worry about that conditional probability because B is not being affected by A because because they're independent of each other. Okay, so this is a simpler form to use. We like to work with independent more than we like to work with dependent. Okay, so dependent, the occurrence of one does affect the probability of the occurrence of the other. So an example of that would be if we have a bag of marbles and I go and I select one of the red marbles out and I set it to the side, okay? When I go back to make the second selection, the pool or the group of marbles that I'm selecting from is not the same as the first time I made my selection because I have one marble missing. That one marble got set to the side, it's not there anymore. So therefore, that one being taken out in the first selection is going to affect my second selection's probability. And that's why dependent is also called without replacement. So if you see the word without replacement, that's an indication that it's a dependent problem. Another one to keep in mind, and this one's a little bit sneaky, but if you see where it says 3 different selections, different implies dependent, because in order for them to be different, you have to make sure that you don't put it back, because if you do replace it, it could be reselected. But if you leave it out, then you're guaranteeing that your selections have to be different. So if you see that it says different, that's another indication for you to treat it as a dependent problem. Okay, if it's dependent, then we have the probability of A, just like we did here, but instead of being able to just multiply it by the probability of B, we have to do the probability of B given that A has already occurred. And we'll work through some examples of these so you'll understand what all this means. Okay, so here's an example of one that I would like to look at. It's very simple, but it does kind of get the idea through as far as the with replacement, without replacement, and so forth. So the first one here, we want to find the probability of a yellow and a blue. We want to do this without replacement. Okay, so if I want to find the probability of a yellow and a blue, and this is without replacement. Without replacement indicates this would be dependent, and since it's dependent, I'm going to have the probability of the yellow times the probability of the blue given that I've already selected a yellow out. Okay, so if I look at the makeup of this container of marbles here, I'm going to select first of all the yellow. So if I look, I've got 5 yellow, and it looks like there's a total of 15 marbles in this container. So the probability of getting a yellow is going to be 5 out of 15. I'm doing this without replacement, so I'm going to take one of the yellows out. When I take it out and I go to decide this probability, I need the probability of a blue, given I took that yellow out and set it to the side. So when I look at this, I've got 1, 2, 3, 4, 5, 6 blue, but I only now have 14 total because I took the one out and set it to the side. So if I multiply out multiply this out, I'm going to get 0.143 for my probability. Okay, if we look at this one, here we want to do the probability of a yellow and a blue, except this time it's with replacement. So with replacement indicates it's going to be independent. So if it's independent, I can just do the probability of a yellow times the probability of a blue. Okay, so the probability of a yellow, we already said, was 5 out of 15. And if I look at the probability of a blue, that's going to be 6 out of 15. Because remember, we took the yellow out, but we also put it back. Okay. So when I do this calculation, I'm going to have 0.133 for that probability. Okay, this one we want to do the probability of a blue and a blue. And we want to do this without replacement. So this one's going to be dependent again. So it's going to be the probability of a blue times the probability of a blue given we selected a blue on the first selection. Okay, so if I look at this, I have 6 out of 15 for the probability of a blue. But if I take that blue away, now I have 5 out of 14. And that's going to give me 0.143 for my probability. Okay, the last one, we want to do the probability of blue and blue. But we want to do this with replacement. So with replacement, it's going to be independent. So I'll do the probability of a blue, and I'll multiply that by the probability of another blue. So that's going to be 6 out of 15 times 6 out of 15 for 0.160. So hopefully this demonstrated to you kind of the idea of the with replacement and without replacement. Okay, here's a couple other examples. This is a drug screening, and these are the results that we get from this. We have 45 positive test results, 5 negative results, and a total of 50. So on this first one here, if 2 of the 50 subjects are randomly selected with replacement, find the probability that the first person selected had a positive test result and the second person selected had a negative test result. So a couple things are going on here. We've got 2 people being selected, and so that's going to tell me that I'm going to have to use the multiplication rule. And with replacement tells me that this is independent. So I need to find the probability of a positive test result and then a negative test result. So because they're independent, I just need the probability of a positive times the probability of a negative. So if I look down here, my positives, I had 45 out of 50. And the negatives, I had 5 out of 50. So when I simplify that, that's going to be 225 out of 2,500. So I'm going to have 0.09. But look at the second one, it's still 2 subjects, so that tells me it's still the multiplication rule. But this time it's without replacement, so that means it's going to be dependent. So if I do the probability of addition, sorry, not addition, probability of a positive and then a negative, then it's going to be the probability of a positive times the probability of a negative given we already had selected a positive. So the probability of a positive, that's going to stay the 45 over 50. But when I go to look at the negatives, the first time I made the selection, I picked a positive. So I still have 5 negatives, but I only have 49 total to pick from. Okay. So that gives me 225 over 2450, or 0.0918. Okay. So it really depends on how you treat these as far as being independent and dependent, as far as how you set these up for the multiplication rule. Okay, we have a special rule, and it's called the 5% guideline for cumbersome calculations. You will definitely know a cumbersome calculation when you see one. If you have to make like 25 parentheses and each one of them is dependent, so every parenthesis is going to be different, that's definitely cumbersome. If you have to write out 3 or 4 parentheses, that's not all that cumbersome. So if it's less than 5 parentheses that you're writing out, I expect you to go ahead and write them out. If it's more than that and it can abide by the 5% rule, then that's fine. So what the 5% rule says is when sampling without replacement and the sample size is no more than 5% of the size of the population, you treat the selections as being independent, even though they may actually be dependent. So that's good because we already looked at independent problems are easier to do. So if we can treat a problem as being independent, it's going to be helpful for us to do that. But we do need to always make sure that our sample is less than 5% of the total size of the population. Sometimes that's an implied thing that you check for. Like if you're selecting like 5 people and that's out of all adults. Well, you may not have actual numbers for comparison, but clearly 5 people out of all adults is less than 5% of the population. So sometimes you just have to use common sense and think through. Okay, so here's an example. On this first one, we're talking about airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 810 scales at JFK and LaGuardia, and 102 scales were found to be defective and ordered out of use. So I want to go ahead and find the probability of a defect. So the probability of a defect is going to be 102 out of 810. All right, so looking at this first one, it says assume that the 2 random selections are made with replacement. So a couple things. 2 indicates we're going to use the multiplication rule. With replacement indicates it's independent. So it says find the probability that they're both defective. So we want the probability of a defect and another defect. So because they're independent, we're just going to multiply the probability of a defect times the probability of a defect. So we're going to get 102 out of 810. And it's going to stay the same for the second parenthesis. And so for that particular calculation, it's 0.0159. Okay, moving on to the second one, we're still selecting 2. This one's without replacement, so it's dependent. So when we do the probability of defective and then defective, because it's dependent, we're going to have to do the probability of a defect times the probability of a defect given that the first one was also defective. So we'll start out just like we did here with the 102 out of 810. So this probability, a couple things to point out here. This probability is going to be the probability for this first that you're starting with. So there were 102 defects out of 810. And however many selections you're making 2 selections. That indicates how many parentheses you need to have when you simplify this. So the first one is 102 out of 810. The second one, we want the probability of a defect given that we've already selected one of the defects. So if I've already selected one of the defects, I now have 101 out of 809. So I have one less defect and one less total in this problem. And so that gives me 0.0157. Okay, the last one, a larger population of 10,000 scales includes exactly 1,259 defective scales. If 5 scales are randomly selected from this population without replacement, find the probability that all 5 are defective. Okay, so the probability of a defect for this one is going to be the 1259 out of 10,000. This one's without replacement, which tells me it's dependent. And it also tells me that I'm going to pick 5 scales, so that's the multiplication rule. So I need the probability that all 5 are defective. So if I'm going to treat this as a true dependent problem, I'm going to start out with the 1259 out of 10,000. And then I'm going to have to go 1258 out of 9,999 because there's one less defect and one less total to select from. And I'm going to do that 5 times. Okay, so when I multiply all of that out, I get 0.0003, actually one more zero in here, 14. One thing about this I want to say is on your calculator, it looks like this. Be careful that you notice this part over here because it's giving it to you in scientific notation. That means I need to move my decimal 5 places to the left. And in moving it 5 places to the left, I get this as my answer. I prefer you to report your answer like this and not like this because this is difficult for comparison purposes. And people tend to say 3.14 is their probability. And hopefully you remember probabilities can never be more than 1. So it's just a good idea to go ahead and convert from scientific notation to your decimal. The exception of that would be obviously if this is like negative 25 and you've got to move it 25 decimal places, then don't do something like that. But otherwise it's okay to go ahead and do that. So this is what we mean by somewhat cumbersome. 5 is not terrible to write out. If this had been 25, which most of the time our samples are going to be larger than 5, then it would definitely have been cumbersome. So if we look at this, we're selecting 5 scales out of a total of 10,000. And if you divide 5 by 10,000, we get 0.0005, which is definitely less than 5%. So we could use that cumbersome calculation rule. And the good thing about that is if we are going to be able to, instead of treating it as dependent, if we can now treat it as independent, then this problem becomes much simpler. And we'll come up here. Because if it's independent, then every one of these parentheses stays the same. So they're all 5 going to be 1259 out of 10,000. And instead of writing all 5 and them identical, we could write it as this to the 5th power. So our answer is 0.000316. So you see that by treating it as independent, we have very little difference than what we would have gotten if we actually wrote all the factors out for it to be dependent. So looking at this, we're like it's way over here before we ever see a difference. So it is acceptable as long as your sample size is less than the total of the population. If it's less than 5% of the total of the population, it is acceptable to treat a cumbersome situation as independent and therefore make an easier calculation for you. Okay, here's another example of one. Here we're selecting 3 adults. So 3 adults indicates it's going to be the multiplication rule. They're randomly selected without replacement from 247 million adults. So 3 out of 247 million is clearly less than the 5% guideline. So we could treat this as independent. We want to find the probability here that that all 3 use drugs. So because we're able to treat it as independent, that means each of our 3 factors is going to be the same. So we assume that 10% of adults in the United States use drugs. So each one of these is going to be 10%, since each of the 3 people are assumed to have a 10% chance of using drugs, which is the same as 0.10 to the third. And so we get 0.001 as our answer. Okay, redundancy is an important part of these probability problems. Our eyes actually have something called passive redundancy, so that if one fails, the other one still is able to see, and that's an important concept in biology. Engineers often incorporate redundant components so that in critical situations, if one were to fail, the other one is there as a backup. So that's kind of what we talk about with redundancy. We increase the reliability of a system by this redundancy idea. Okay, so here's one. Modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight control is maintained with another functioning system. Okay, so in this particular example, we're going to assume that the probability of a system failure is going to be 0.002. So if the Airbus 310 were to have one hydraulic system, what's the probability that the aircraft's flight control would work for a flight? So the probability that it fails is 0.002. So the probability that it works is going to be 1 minus the probability that it fails. So 1 minus 0.002 is going to be 0.998. So we have about a 99.8% chance that the airplane flies correctly, there's no problems, and everybody, is able to go ahead, be safe in their flight. The question becomes, when people's lives are at stake, is 99.8% good enough? So if we were to increase the number of hydraulic systems, let's see how that improves the safety of the flight. Right, so on this one, again, we're using the same failure rate. Given that the Airbus 310 actually has 3 of these independent hydraulic systems, what's the probability that on a typical flight, control can be maintained with a working hydraulic system? So before we do the calculation, I want you to think about this a little bit. We've got 2 scenarios. Okay, either the Airbus flies safely, has no system failure, or it has some kind of safety issues. So when we look at those 2 scenarios, the only way that it has a safety issue is if all 3 systems fail, because if one of the systems works, it's fine. Okay, so as long as at least one system works, and then it's not going to have a failure, and it's going to fly safely. And that's what we've got to find the probability of here. When we look at this, the probability that all 3 systems fail would be the probability of a failure raised to the 3rd power. We assume our systems are independent because if they were dependent on each other and one failed, then it's going to wipe out all the rest. So they have to be independent with this. So the probability that they all 3 fail is 0.002 to the 3rd power. So the probability that it's going to fly safely with no system failure is going to be the complement to that. Okay, so we're going to look at 1 minus the probability that they all fail, and that's going to give us the probability that at least one of them is going to be working. So we have about a 99.999999, and I may have missed a 92%. So we went from 99.8% to this number here. So we get a lot more accuracy by increasing the number of components there. So again, we want to find the probability of at least one system working. That's the complement to the probability that they all fail, because the only scenario that causes problems is if they all 3 fail. Okay, and so this is just kind of working this out. Okay, here's an example that I would like for you to try dealing with your alarm clock. So if you'll pause the video and try this one and then check your answer. Okay, these are the answers that you should have gotten. Assume your alarm clock has a 0.9 probability of working on any given morning. So the probability that it will not work would be the complement to that. So 1 minus 0.9 will give me 0.10. If you have two alarm clocks, so it's a probability that they both fail. So we found out the probability that one of them fails, and we want the probability that they both fail on the morning of an important final exam. So we're assuming, again, they're independent. When you have redundancy, you basically assume they're independent. So the probability that they both fail would be the probability of a failure times the probability of a failure, which gives us 0.01. On part C, the probability that you'll be awakened. What's the probability of being awakened if you're using two alarm clocks? So you're going to be awakened if one or two of the alarm clocks work. So basically, the only scenario you're not awakened for is if both fail. We've already found that probability here, the probability that they both fail. So the complement to them both failing is that you're awakened by at least one of the alarm clocks. So that would be 1 minus the probability that they both fail. So 1 minus 0.01 from our answer here gives us 0.99. I want to ask the question, why not just multiply the probability that each one works? Hopefully you can think about that for just a minute. Okay, if I look at this, what this actually is the probability that one works times the probability that the other one works. So it's giving me the probability that they both work, which is not what I'm asked to find. I'm asked to find the probability that you're awakened for your exam if you're using two alarm clocks. It would be great for them to both work, but you're still going to get to class if one or the other of them work. So this, multiplying these two together, is going to give you the probability that they both work, but it doesn't take into account the probability that one of them works and the other one fails. So that's why you have to do the calculation for part C like this, not like this, because this is not going to give you the right answer. Okay, here's another one that I'd like for you to try and then check your answers. Okay, check your answers for this one. You're asked to find the probability that you're going to have 20 females among 20 babies simply by chance, and that's a way of checking the to see if this procedure works. So if we're going to have 20 babies, we want the probability of 20 females. So each birth is represented here by the probability of a female. So we want 20 females. So we need the probability of a female 20 times. Because these are independent, births are independent of each other. This is an independent situation. We'll just do 0.5 and we'll do that 20 times. So 0.5 to the 20th gives me this probability here. Okay, as far as how I interpret this, does the resulting probability provide strong evidence to support the geneticist's claim that the procedure is effective in increasing the likelihood that babies will be females? Okay, if I look at this probability here, it tells me it is extremely rare because remember, 0 is impossible as a probability, and this is very close to 0. So it's nearly impossible to have 20 births and get 20 females just by chance alone. So if I am getting 20 females among 20 babies being born, then it's pretty compelling evidence that this procedure is responsible for increasing the likelihood of female babies. Okay, so to summarize here, we looked at the addition rule and the multiplication rule. So just be comfortable with using each of those and understanding the situations that you need to use those in.